You think about arc length, we talk about arc length being the length of a segment of a curve. And in geometry and in trigonometry, we talked about it on a circle and the length, a piece of a circle. It's a distance, so we can approximate it using the distance formula, which I'm sure you recall is this. So we can approximate it using that because we don't have straight lines, and we'll look at some pictures in a minute. A rectifiable curve is a curve that has a finite arc length. And we say it's sufficient one eye. It's sufficient for F to condition, a sufficient condition for F to be rectifiable between the points. So I have to give you some points, AF of A and BF of B, if the derivative is continuous. On the interval from A to B, the closed interval. So when we're looking at a distance and we're approximating it, think about a curve. Okay, and I'm looking at some distance here, right? I have a little triangle, so I have a delta x and a delta y. And remember, this is a line, so it's not actually the curve. Think about derivatives. So we're looking as delta x and delta y go to 0. That's what we're interested in. We're getting them smaller. And then what we're going to do to find the arc length is to add up a lot of the little segments. So it's a sum, right? It's a sum, and as the distance gets smaller, so you see how it's going to look like an integral. So if I have 2 points, xi minus 1, yi minus 1, and xi, yi, I know that my arc length is a distance, so it's the distance of using a distance formula from between those 2 points. And this is just delta x at that point. This is just delta y at that point. Now, what happens if I and then it's squared because inside there is squared, but that distance is squared. So I can say that s really equals, I'm going to pull out a delta xi squared, and now I have a 1 here, and here I have delta yi squared over delta xi squared. And if you recall from the mean value theorem, I have points so that I have some function, a c, in that interval xi, my interval from xi minus 1 to xi, I have some ci in there, so that the derivative equals my change in my y over my change in my x. We go back to the mean value theorem, think about what it is. It's because we're just using the approximation of a slope, using the point slope form. So this is the same as my delta xi squared times 1 plus the derivative at some ci squared, and the square root of that. Okay, so when I want to, now I'm looking at a limit of a sum, so the s is the limit as my deltas go to 0 of the sum of all these little pieces. So it's the delta xi, because the square root of delta xi is square root of delta xi, and then times the square root of 1 plus the derivative at some point in that area. So I can then, when I simplify it, really what we're saying is we'll get to the definition of arc length here, which is if I have a function y equals f of x, and it's a smooth curve on the interval from a to b, the arc length of f from a to b is s, which is integral from a to b of 1 plus f prime of x squared dx, because remember, delta x is dx, and this is what we have here. Okay, similarly, if it was a function x, a function of y, it would be the same thing.